Okay, so right now I'm going to talk about projectile motion. I'm not going to be going through any specific problems. I might make a couple up at the end, but we're just going to have a general discussion of projectile motion, how we use calculus to describe it, and what kind of techniques we can use to get through problems. And so when we do the problems we're talking about here, we're usually going to be talking about some sort of vertical motion problem, which means that for the most part, you're going to have a time axis here, and you're going to have like a height axis, or it might be x, it might be displacement in this direction, but it's not x, y, it's t, and either y or x, some sort of displacement. So, if you have something like this is going to be a clue that, you're moving at some sort of constant speed. And the reason that's so, okay, we define speed to be distance per time. Okay, if your speed is 10 miles per hour, then you're going 10 miles in 1 hour. Makes sense enough, right? So, and just for the sake of things matching up here properly, I'm going to call this velocity. Velocity equals distance over time. Speed doesn't have a direction to it. Velocity does, because it's a vector quantity. And so that means that you can have a negative velocity. Negative 15 kilometers an hour means 15 kilometers an hour in the negative direction. And so that would probably mean you're going backwards. So I'm not going to use that speed thing. We're going to say velocity is the distance per time. So in other words, velocity is the change in x, if that's your distance unit, over delta t. And that's basically slope, right? Slope is y2 minus y1 over x2 minus x1. You can also write that as delta y over delta x, your change in y over your change in x. And so that's why when you look at a graph like this, if you have something t here, and that matches up with some if that matches up with some x there, I'll start using x. Then the slope of this graph is x over t, or the change in x over the change in time. And so that means your slope is equal to the velocity, right? So that's why you're getting that intuition that the slope on an x versus t graph gives velocity. Okay? All right. So now, but what if we're not straight? What if we're curved? Then, our speed is increasing. We have different speeds at different times. And so if you have some tangent line there, you can look at the slope of that. And that quantity, all you have to do is take those deltas. Sorry, I won't use y because that was just the slope thing. All you have to do, so you have your delta x over delta t. All you have to do is take delta x to 0, which will take delta t to 0. It's kind of the other way around. You take delta t to 0, which will bring delta x to 0. And then you take delta x over delta t, and that gives you your derivative. And you end up with dx dt. Okay? So dx dt equals v, the velocity. Okay. So the derivative of x with respect to t is the velocity. And so we're going to keep this in mind. All right. So then if we look at the velocity for something that's, if you have an x versus t that's just constantly increasing. So, if after 1 minute or after 1 second, I've gone 5 meters, 1 second, 5 meters, 2 seconds, 10 meters, 3 seconds, 15 meters, etc., then you can tell that I'm going 5 meters per second. And so the slope would be 5 meters per second, or dx dt equals 5 meters a second, which means that v equals 5 meters a second. And so then if I look at a velocity versus time graph, like we have before, and this is just looking at the derivative graph, this is the velocity, this is time. Velocity versus time, we're just going to have it like that at 5. So v equals 5 meters per second. And so as time goes on, the velocity does not change. And so that's moving at a constant speed. It makes sense. Constant velocity. I should stop saying speed and keep saying velocity. I'm sorry. But if we're curved, like we are here, then this function is concave up, which tells us that our velocity is going to be increasing. And so you'd have something more like this. That's our velocity. And our velocity is going to be the derivative of the x function, dx dt. And then what acceleration is kind of a tough thing to describe, and eventually you'll just hit a point where you're like, oh, that's what it is. It's the change in velocity over time. So I'm going to tell you that acceleration equals the change in velocity over time, dv dt, if you take it to an infinitesimal level where you're looking at derivatives. And so if we look at this, our acceleration is going to be the slope of the velocity graph, right? And when we do these, when you're dealing with like projectile motion, you're always, you're either going to have a constant velocity or an increasing velocity. You're never going to have like concavity on your velocity graph, because that means you have a variable acceleration, which the Earth doesn't give you. So unless otherwise specified, you're not going to, get anything more complicated than this. So your acceleration is the slope of your v graph. And velocity comes in meters per second, and time comes in seconds. And so if you do v over t, you get meters per second, which we write as meters per second squared. Meters per second squared, if you look at that, you kind of go, what the heck does that mean? But think of it as meters per second, which tells me that every second, the velocity increases increases a meters per second. So if my initial velocity is 0 and my acceleration is 5 meters per second, 5 meters per second, at t equals 1, at t equals 0, t equals 1, t equals 2, and t equals 3. At t equals 0, I'm going to be going, I'm going to be going 0 meters per second. At t equals 1, well, after 1 second, v increases by a meters per second. So after 1 second, for every second, v increases 5 meters per second. So now the velocity is 5 meters per second. And then at 2 seconds, it's going to be 2 times the velocity, because after 2 seconds, you increase 2 times whatever you would for 1 meter per second. So now the velocity is 10 meters per second. And then finally, you have 15 meters per second. And so you have an increasing velocity. And so your velocity graph is going to look like this. And the slope equals 5 meters per second. Or the slope equals 5 meters per second, if you take the units into account. And so that tells you that you have a constant acceleration, because your acceleration is always 5 meters per second squared. So if I do a little sketch of that over here, that's just going to be another one like this, where it's just constant like that. You're not going to deal with any accelerations that aren't constant until way later in the year. So, dealing with projectiles now, Earth's gravity provides an acceleration of minus 10 meters per second squared. And so that's saying that if I have the Earth here, then if we put a little coordinate system on it, it's a terrible coordinate system, but that's okay. If this is the y direction, and this is the negative y direction, well, gravity pulls us down, right? Gravity accelerates us downward. If you jump off a building, you pick up speed because you're accelerating. And so gravity exerts this force downward on us. And the magnitude of that force is 10 meters per second squared. Approximately. It's 9.8. That's not a 9. 9.8 meters per second squared. But it's approximately equal to 10. And a lot of the time when you do quick calculations, a lot of the time you use 10. For the AP test, they'll have you use 9.8. So 10 meters per second squared. And it's going down though, and so the acceleration is negative, whatever that is, because it's accelerating you in the negative direction. If you orient yourself, if you orient your coordinate system so that for some odd reason up is negative, then your acceleration would be positive 9.8 meters per second. It's all about the way you orient yourself. And so sometimes you'll run into a problem where it's like, where maybe you have like a cliff or something, and you're dropping something off the edge of the cliff. You have a couple options. You might be able to put your coordinate system right here. Let's say this is 100 meters high. You might be, you could say that this point is 0, 100, or you could put your coordinate system up here and say that it's at 0, 0. And it really just depends on what you're doing. But just keep in mind that you need to pick a place where your origin is going to be, and you need to pick positive and negative directions. I mean, usually when we do these, it's pretty clear that, up is going to be positive and down is going to be negative. But just be careful with that, because it's really easy to get signs flipped around. So be cautious of that. All right, so hopefully that gave you a little intuition about what, the relationships of derivatives in these graphs. And also it follows that, when you integrate acceleration, you'll get velocity. And when you integrate velocity, you'll get the position. And this video is almost like 15 minutes long right now, and I don't want it to take like 45 minutes to upload. So I'm going to go ahead and cut this one right now. But I'll go ahead and make another video in which I'm going to derive the motion equations that you're using and explain exactly why those are the way they are.